started here. Suppose I can put that away and talk about the general ideas that we're going to work with next year. So when we ask the question, what are we doing in statistics? What is the purpose of statistics? And Sierra, I think you're on restriction for this. So what's the purpose of statistics?
5% or less. No.
Okay, 5% or less.
95% or more. Yes.
Yes. All right. And what phrase do we use to describe that? This is what to expect. What other phrases do we use to describe it? Data-driven decisions, right? So what are the two methods of doing data-driven decisions? Okay, confidence intervals and hypothesis testing. So what do we do when we have confidence intervals and hypothesis testing?
Measure population.
Okay, so for confidence interval, we're doing a measure of the population. What do we do in hypothesis testing?
Prove the difference.
Prove the difference. Now, what we have done in past procedures that we've been doing here is that we have used a couple of different types of data. The first type was a single sample. Notice that we are considering populations here. So with hypothesis testing, prove a difference of populations. But we're using a sample in order to prove something about a population. We do have things with a single sample, and we had P X, well, yeah, let's say P hat X bar and S. So those are our sample numbers, and we were proving something about P, mu, and sigma. The proportion, the mean, and standard deviation. Now we also talked just a little bit about situations where we had two samples. And recall that we can do confidence intervals for any of these things. And we can also do hypothesis testing for any of these things. And then what we're going to be having to test on is two variables. Or ordered pairs where we have X and Y. And when we're dealing with this, just about all the time, we're talking about the mean of Y for X. But we also are able to do data values of Y. So that's something more with when we start talking about X and Y measurements, we say I can actually predict what my data is going to look like, not just where the center of my data is. So that tends to give us maybe more information. It helps us to make better decisions because we're not just talking about one measurement, we're talking about a relationship between measurements. So we say something like, if you give people vitamin C, will it change their blood pressure? Or what dosages, you know? If you say, how much vitamin C do you have in your system? And what's your blood pressure like? You can measure that effect and you can make things happen, okay? Well, what we're going to do now is we're going to take all this stuff and we're going to kind of put it together. We're going to do a mashup, as they say, right? And so we're going to have multiple samples. So instead of just doing one sample, we might do 8 samples, and we're going to be comparing them all. And so we say, well, if I'm going to do that in samples, I need to have some way that's going to allow me to do that. And we have proportions, and we'll have 2 different kinds of things here. If I A proportions, then little 1 and little 2, okay? So I'm not going to tell you what they are yet, but I'm about to. And we're going to have different ways to compare proportions. And then we are also going to have comparing means. And this is the thing which is called ANOVA. And that'll be our last topic. But this thing that we're going to be doing right now is going to be similar when we were talking about 2 variables, because now that we have multiple samples, it's possible that we might be able to figure out if somebody has, let's say, they have 1 car in their family versus 2 cars in their family. And then we say, is that related to like mental health? Whether you have just 1 car or 2 cars. And so then we can have like different categories of people, and we're going to be measuring proportions of people with different kinds of car, different numbers of cars, and people with different conditions. And so then we'll say, all right, so is there a relationship between these things, which is what we were talking about here when we did X and Y. So it's using proportions, but it's also putting that together with the idea of relationships between things. We'll get to that eventually. All right, so then, the first idea that we have with proportions, when we're talking about multiple proportions, this is called goodness of fit. And then the second thing is called the test of independence. And I put it in quotation marks. And I'll talk about that later. So these are the first 2 things. We're talking about proportions and the relationship between them. There are 2 different things to do. So then, we have to be clear about which one is which, right? What are we given? And we're going to go through and do the entire goodness of fit thing. And then we'll come back and do the other. So for goodness of fit, we are given a list of proportions. So the only way that this works is that if we have some kind of an idea before we even start the problem, we have to have this idea of what relationship of different percentages or probabilities. It has to be given to us. So, for example, let's talk about what you might want on your salad. Salad toppings. And so you walk in and you're sitting down and they say, okay, we've got some options here for what you could have on your salad. And we're going to go with tomato, onion, olives, and butter. And we're going to let you pick one. All right? So let's see if we can get some votes here. If you had to pick one of these, how many of you would pick tomato on your salad? 1, 2, 3, right? So let's say 2. How many of you pick onion on your salad? 1, 2, 3, 4, 5, 6. That's 20. How many pick olives? There's a few brave souls, so that would be like 4. So let's go with 15%. So the rest of you are in the other category. 10, 20, 30, 45, 50, 55%. Okay? So let's say that you are in the food service and you say, I want to know what people like. And then this would be our given list of proportions. Now, we're going to use the letter P for this. That these are the population proportions that are given to us before we start asking. Okay?
Is that actually the letter D, just to clarify?
Yes, it's actually the letter P, and it's a small letter P. Even though it's hard to see that here, it is. It's a small letter P, okay? So these are the population proportions, and so I did my little survey of you guys. You guys are going to now be my standard. You are the standard people. But then I go out and I compare this to a sample, okay? And what I'm going to have are called observed values. And what I'm going to write down here will be the frequency, not the percent, but the frequency. The number of people that are in these categories. Okay, so I'm going to make this happen here to be 0.10, 0.20, 0.15, 0.55. And so we're going to have, let's say, 40. 50, 60, and 50. All right. So we're going to go out there and we're going to say, we're going to ask like people actually going through the cafeteria. And we'll get some numbers. Let's say it's 40, 50, 60, and 50. So we are given an initial set of percentages that's like our national number. Okay? And then observed frequencies, these come from our sample. And then we say, I want to know how this works. How can I tell what's going on here with goodness of fit? Well, first of all, what do we always start with when we're doing hypothesis testing? Null and alternative hypotheses. So this is the null hypothesis for goodness of fit, is that our population proportions fit the ones given to us. So that I say my group, whoever they are, is the same as somebody else's research or some other thing that I've said is a certain way. And then the alternative is at least one population proportion is different from the given. That's why it's called goodness of fit. Does it fit? Does my group fit what I thought it was going to be? I thought they were going to have these preferences. But then I say, do they or do they not? I don't know right now if they fit or if they don't. Okay, so you would think, right? You would think that what we would do would be compare proportions. And so we'd figure out proportions for all of these. But that's not what happens. What we're going to do is we're going to create a list of expected frequencies. And we have a formula to do that. E is equal to N multiplied by P. Now you may recognize this from when we did binomial. That's what it is. So the question is, how do I know N? What is my sample size here? Anybody have an idea? Where am I going to get my sample size? If I add together my observed values, then that'll tell me how many people did I talk to, the total. Okay, so what does this add up to be? 200. So in this case, N is equal to 200. Well, what are these values of P over here? Those are the ones that came from the previous research. So I'm going to take each one of these percentages as a decimal number, multiply it by 200. That will give me my list of expected frequencies. All right? So what's 200 times 0.1?
20.
Okay. Is right? I think so. Okay. I don't like it. So I'm going to have to change that to, so if I make this That'll change things. Yeah. All right. So I want to make that different here. So we'll make this 88 and this 120. Nope. 70. Nope. 60. 140. Yeah, that'll work. Okay, so sorry, I had to change the numbers. This is 30, 70, 60. Is that we observed? Yes. 30, 70, 60, and 140. So this is now 300. All right, that's right so far. So now these numbers are going to change. So I changed the frequencies. So now I have a number down here at the bottom, which is 300. And I told Julia earlier today that I make mistakes in class just to make sure that everybody knows that I'm not that smart. So we're okay so far. So then if I take 300 times 0.10, this would be 30, of course. This comes out to be 60. This would be 45. And then that would be the rest. $165. All right, so that looks better. Did I come out exactly the same, observed versus suspected? No. The question is, how much of a difference is there? Is there enough of a difference that I can actually prove that they are different? So in order to do this, we're going to use hypothesis testing. So we're looking at this and we're saying, I know what I thought it was going to be. I thought it was going to be 10, 20, 15, or 55%. So therefore, for 300 people, I thought it was going to be 30, 60, 45, 165. But that's not what happened. My numbers are not the same. Is this just a random fluctuation? Or is there a real difference here between what I thought it was going to be and what it actually is? It looks like I've got more olive-loving people than what I expected. But is that a significant difference? Should I plan on ordering more olives for my restaurant? We're thinking about how that's going to work here. So, now that we have this, what's the next step in hypothesis testing? Okay, so we're going to look at critical values here. And what we're going to use is chi-squared, table G, and degrees of freedom is not n minus 1. Degrees of freedom is not n minus 1. It's k minus 1. K minus 1 is the number of categories minus 1. Categories doesn't start with K, but it sounds like a K, right? So categories minus 1. Here we have 3 degrees of freedom because we have 4 categories. So you need to find table G if you've got it there. And I want my critical value. And specifically, this is always a right-tailed test. So I'm looking at table G, and I've got how many degrees of freedom? 3. So I want my chi-squared. What do you think we should use for alpha? 0.05. So if I have 3 degrees of freedom and I have 0.05, what is my chi-squared number? 7.815. All right? That is my critical value. 7.815. So over here, I shade that part in that direction. All right, well, what's next? Goodness of fit is always right there. So what happens next? What's my next thing to do in my hypothesis testing?
Test value.
Test value. Here comes the formula for test value. Chi-squared is equal to the sum of O minus E squared divided by E. So, what do you think O stands for? Observed, and E would be expected. So we're not actually working with proportions here. We're using the frequencies that we have, and we're comparing it to the frequencies we would expect. And we put them into this formula. How many times do I have to go through this calculation? 4 times, because I have 4 categories. So it looks like this. 30 minus 30 squared over 30. 70 minus 60 squared over 60. 60 minus 45 squared over 45. And 140 minus 165 squared over 55. So I have these 4 calculations that I need to do. Now, for some of you, calculation was a problem on your previous test. There's not a lot of calculation on this test, but there is some coming up here. So you need to be aware of the whole order of operations, putting things into your calculator, all that good stuff, right? So here, you would do the subtraction, find out what that is, square that number, and then divide it by the number that's on the bottom. Now, the first one's easy. It's just 0. 30 minus 30 is 0. So this is 0. Let's do these to decimals. Let's go out, let's say, to the hundredths place. So what do you get for the next one? Abby, you got some?
Yes.
Okay. Rachel, you got something?
Yes.
Okay. Casey?
I have 0.
The second. I got 0 for the first one. I'm already at that. I want the second.
How far do you want the decimals?
Hundredths place. You got something there, Jessica?
So 1.67.
1.67. Okay. What's the next one?
5.
5. What's this?
3.79.
3.79. And then the formula says, add them all up. What do we get when we add them all up? Did you say 10.46? Yep. Okay. That is our test value. Well, what does that do for us? What's our next thing after we find the test value? Okay, how do we go about making a decision? Okay, Hillary, can you tell me what decision I'm going to make here? I'm going to reject the null hypothesis because the test value is in the rejection region. Okay, so 10.46 is out here. So that means we're going to reject the null hypothesis. However, we have a problem when we do chi-squared goodness of fit testing. When I look at this right here, and I say, what do I know now? What does this tell me? Okay. If I reject the null hypothesis, what's my next thing to do? Hillary, can you tell me? I confirm or prove, or there's evidence for the alternative. But my alternative doesn't actually tell me a whole lot. My alternative just says there is some difference. At least one of these numbers for my population proportion in my group that I surveyed is different from the national number. But I don't know which one it is. All I know is that there's something different. Well, how can I tell? I can't. There's no further hypothesis test that I can do right now that will tell me anything about a difference. But what I can do is I can make confidence intervals for all these things. So that's what I'm going to do next. So based on these things, I'm going to create a p hat. P hat is going to be the observed over the total, right? This would be x over n. So it's 30 over 300, 70 over 300, 60 over 300, 140 over 300. This I know is 0.10. The others I have to look up here. So that would be approximately 0.23. That one is 0.2. And the other one's 0.47. Are these numbers significantly different from the national numbers? Well, according to chi-squared, yes. There is a significant difference here somewhere. Well, where is it? I don't know. But I can make confidence intervals. Now, what's going to happen then is that I myself will do the confidence intervals for you on the test, so you will see what they look like. All right? So I'm going to pull the screen down, and we're going to look at, actually I'm not going to pull it down. Pull it down a little ways. But I'm going to put these things up on the screen and see if they can make sense. And we won't take a lot of time with this because we have more time next time. but I want to show you what it is, and then we'll explain it more thoroughly next time. All right. So here we have the information. And I might be able to move this around a little bit. So you can see it maybe a little better. Zoom in a bit. Okay. These were my national proportions. P hat, these are my observed proportions. And then right here is my confidence intervals. The lower and the upper numbers. And what is that telling me? I erased it, but what is the purpose of the confidence interval? Emily, can you tell me the purpose of the confidence interval?
To describe a measurement of the population with some degree of confidence.
That's correct. So this right here, based on my observed number, these confidence intervals are population numbers for my group. I want to know if my group is different from the national numbers. And right now, I know that the tomato-loving people in my group is somewhere between 7 and 13. But that's not really any different from 10%, because 10% is part of that group. So I don't know whether my people are lovers or haters of tomatoes, because it's not different from what I had over here. But what about the olive people? This is the national number for olives, 15%. This is my confidence interval for olives, 16 to 24. This is for my group. Is my group more than this national number? Yes, it is. Because 16 to 24, any of those numbers would be more than 15%. So now I can do a conclusion. I've actually proved a difference using a confidence interval. So what I can now say is my group has a higher population proportion for olives than the national group. So when I look at this and I say, is there some difference? According to chi-squared, there is some difference. What is the difference? According to this, my group likes olives more than the national number.
Would you go on to also add that your group uses other less than the national average?
Has a lower population proportion for others. I can't say anything about tomatoes because it's in that interval, but I can say that this is my group, and they are higher in this category. They're lower in this one. What about onions? Well, 19 and 20 are actually pretty close to each other, right? So maybe I'll change my alpha or something. Because this, I had to use alpha in order to use confidence intervals. Maybe I'll just see if it's close or not. But right now it's kind of higher. Since my confidence interval is from 19 to 27, and I say 20, well, that's almost down there at the low end. So this is almost higher than 20. So I'm going to say kind of. Now, I said to you a while ago, there are a lot of people who do research who say that confidence intervals are the right way to do statistics. And so they would say this chi-squared stuff is just crazy. So that what you would actually do is you'd work with the confidence intervals all the time. So then the confidence intervals give you more information, right? Now I know specifically what things to order and what things to not order, maybe, because my confidence interval tells me the population proportion is higher for olives. The chi-squared could not tell me that. It could just tell me that something was different. So that's one reason why confidence intervals are used maybe more now than they used to be, because they give you better information about what's going on. All right. I hope that's enough for today. There's quite a bit more that we'll need to do the next time we get together. But for right now, we're going to take a 10-minute break, come back at 1:50, and have test number 2.